she's a rising star, and she has many awards to her name, including the NSF Career Award. And recently she spent a year at TU Berlin with the Humboldt Fellowship. So her research interests are in numerical analysis and scientific computing, inverse problems, computational image processing, numerical linear algebra and optimization. Today she's going to give what I think is an overview talk on computational advancements in large-scale inverse problems. Julianne, whenever you're ready, please get started.
Can you hear me okay?
Sure yeah, we can hear you, yeah.
Okay, awesome. And then hopefully you can see the slides too. Okay, hi everyone, and welcome to the session on large-scale inverse problems and UQ. I actually want to begin by thanking John for the very nice talk and for helping to set the stage regarding some of the main challenges, recent work in the area of inverse problems and UQ. My goal in the next half hour or so is to tell you about some recent advancements in the field of iterative methods for solving large inverse problems, in particular in the area of hybrid projection methods. Before I begin, I would like to acknowledge that this is work that has been supported by the NSF, and I'm very grateful for their support. Okay, so I know the audience today might be quite broad, so I wanted to start with some motivating examples. We already saw some in John's talk, but a few more, and then describe the general ideas underlying hybrid projection methods. Then, because I know it's been a long day and I don't want anyone to get too lost in too many details, I'll give an overview of 3 of my recent projects. All of these are in the field of hybrid projection methods. And for each of them, I thank my collaborators, my wonderful collaborators listed here. Okay, so let's start with some examples. This one. So we saw this example in John's slides, but essentially an image deblurring, you're given a blurry image like the one you see here on the right, and you know something about what caused the blur in the image, and the goal is to solve the inverse problem to reconstruct the true image here on the left. So this is also just to set up some notation here. The blurred image is given by D here, the observed image, which has some noise in there, this epsilon here. And the true image, which is what we want to reconstruct, is this S true. And typically, because we can exploit some structure in that blurring process, this A matrix, although it is quite large, it is very structured. So just to give some indication of size, if you're trying to solve for an image, which is say 256 by 256 pixels, right, your matrix A is 65,000 by 65,000. Now, if you then start talking about solving for 3-dimensional images, right, then you have the number of unknowns can be up in the millions, right? So these get to be quite large problems. However, oftentimes we're able to exploit some structure or sparsity in our matrix A so that this operation, this blurring operation here, can actually be done efficiently. All right, so another example arises in photoacoustic tomography, which is a non-invasive, non-ionizing biomedical imaging modality. It's based on the photoacoustic effect. And the idea is that you have these laser pulses that enter into some biological tissue. It's absorbed and converted to heat, resulting in some expansion. And so what happens is you have detectors that are located outside the object, right? And those detectors are essentially circling the object. So it's the same idea underlying modalities such as X-ray and computed tomography. So the idea is you're given all of these observations at all of these different points, and the goal is to reconstruct the initial pressures or what's inside that object of interest. Now, the key difference here is that we're actually looking at something called time-lapse photoacoustic tomography. So in time-lapse, what's going on is as the detectors are moving around the object, that object might actually be changing. And so the problem is if you take all of the data and do a reconstruction, you might get some artifacts, perhaps motion artifacts or other types of artifacts if that object changes during the data acquisition time. So the idea underlying these dynamic problems or these time-lapse problems is that instead of just one, say, image that you want to reconstruct, you want to reconstruct a bunch of images in time. So here you would have, for example, each image is, say, 256 by 256, and then you have, say, 120 time points. So if you look at all of the unknowns that you need to solve for, you have about 7 million unknowns here in this as true vector. Now, because each of the observations, right, would correspond to one of these vectors, this D1 to DNT, you'd have essentially one radon transform corresponding to each time point. Okay, so actually I wanted to show, let's see if this will work, a video. I'm not sure if you guys are seeing this.
We can see your iPad, yeah.
Oh, but you don't see the...
Not yet.
Okay, well then maybe let's try a different approach. Well, this might not work. Let's see. Technical difficulties. All right, so let me try again. Let me try again with the probably not, huh? Okay, well, we'll have to table that then. Oh, no, I think you have it now, right? There's a video of, on the left, you see the image changing in time, and you can see that in time things are coming in and out of the screen, right, in and out of the visual region. And then on the right, you can see the observations that are occurring in time. So this right here, we would essentially call the sinogram, right? These would be your observations. And the point is that you don't want to just reconstruct one of these images, you actually want all 120 of the images that you see here on the left. Okay, we'll go back to this. Oh no. There we go. Okay, so the idea with the dynamic tomography is that given these observations, in this case we have 43,000 of them, we want to reconstruct the 7 million unknowns in the S true. So you can see the different images in time here at the bottom. Okay, so the main point here is that the number of unknowns here could be extremely large, right? And so oftentimes the matrices that we are dealing with are also very large. So we need methods that can accommodate these challenges. All right, so all of the problems that I was talking about, these are linear problems. Of course, we could talk about nonlinear problems and the associated challenges, but we're going to focus on linear problems here. Also, because oftentimes when you're solving a nonlinear problem, it reduces to a linear problem that needs to be solved. Actually, as we saw in John's talk, that at the end of the day, there's always some large linear problem that needs to get solved. So we're going to focus on the linear problem here, where we have some assumption on our noise. In this case, we'll assume it's a Gaussian with, say, 0 mean and maybe some covariance matrix R, which for our case, we're just going to assume that this is something simple like a diagonal or a scalar times identity matrix. So the inverse problem is given the right-hand side D as well as knowledge of your forward model in this A matrix, we want to compute an approximation of this as true. All right, so the typical approach for solving inverse problems is to include an additional regularizer, like you see here, where here lambda is our regularization parameter, R of S is some regularization operator, and we're going to use because we have this additive Gaussian noise, we're going to have this data fit term, which is essentially a variant of least squares. All right, so the practical things we need to keep in mind, especially when we're solving large scale problems, is that first of all, the number of unknowns in S might be very large, especially in these dynamic problems, right? We're dealing with millions of unknowns in S. We need to have methods that can that do not require the actual matrix A, because this matrix A could actually be large, but instead methods that can take advantage of efficient matrix vector multiplications with A and say A transpose. So it might be that A is a Kronecker product. It might be block diagonal like we saw in the dynamic PAT example. It might just be a function evaluation, right? It might just be a black box that you have an input and an output. This choice of the regularization term, there are a lot of different methods out there of ways of how to choose a good regularization term. Oftentimes this comes from some prior knowledge that you have about your problem, from some expert knowledge, or even nowadays from some training data that you may have. So these data-driven type of regularization terms. And then, as usual, we have these regularization parameters that need to be either selected a priori or estimated during the solution process. So there have actually been quite a few, there's been a lot of work in this area, and there have been some special issues out there on tackling the different modern challenges that arise in imaging problems where you need to be able to solve very large inverse problems. And so here's just kind of highlighting some of the ones from inverse problems. Okay, so what are hybrid projection methods? Well, I'm going to explain it for standard Tikhonov regularization, but then I will give you an overview of some extensions of these hybrid methods. But just so that we all are on the same page of what is a hybrid projection method, let's talk about standard Tikhonov regularization, where you have the regularization term here, which is quite simple, right? So you have the regularization parameter lambda, you just have the norm of your solution S. So essentially you want to enforce some smoothness properties on your solution. Now, assuming you could compute the SVD of A, which, as I said, in the large scale problems, you can't do that, but just for a small example here, suppose you could compute the SVD of A. Then if you look at the singular values, so you have your singular values sigma 1 to sigma n, typically you're going to notice that those singular values have a decay, oftentimes a slow decay without a huge drop. And oftentimes you also have a bunch of small singular values. So a lot of singular values that are essentially clustering around 0. By definition of SVD, you know that the U and V matrices are orthogonal matrices. And you can actually, it's a very simple exercise to show that the solution to the standard Tikhonov problem can be written as a filtered singular value decomposition, filtered SVD solution. So here the solution S sub lambda can be written as a filtered SVD solution, where the filter factors here are given by sigma I squared over sigma I squared plus lambda squared. So here, right, these sigma i's are your singular values, right? So your singular values, and then this lambda is the regularization parameter. Now, there's a lot of work out there on how do we choose this regularization parameter, and there was a little bit of talk on that in the previous talk about, well, maybe we can use a MC-MC approach. Kind of the classic approaches for choosing the regularization parameter go back to simple things like the discrepancy principle, where you say, I assume I know something about my noise, right? Maybe I know the noise level or the type of noise that I have in my data. And so I'm going to use that to compute, so choose a regularization parameter lambda, such that, say, my residual norm is something close to the noise in my data. Another very common approach is called the generalized cross-validation method. Essentially, it's based on the idea that you have a data set and you leave one data point out. Well, a good regularization parameter should be able to predict that data point that you left out, and you do that for essentially all of your data points, and you get this nice formula. This is called the GCV function, and the idea is that you want to choose the lambda which minimizes this function here. So you can see the numerator is not too bad, that's just the residual term. The denominator is a little bit more tricky because you have this trace term. Another common example of a method that people use to choose regularization parameters is the unbiased predictive risk estimator, UPRE, and it's very similar to the GCV idea in that you essentially need to find the regularization parameter lambda, which minimizes this UPRE function. Okay, so I should say that for smaller problems where A is small enough so that you can compute the SVD, evaluating these functions here to compute a regularization parameter are fairly simple. I mean, you can do it. But for very large problems where A is too large, you know, to really work with easily, using these methods can become challenging. Another common approach for solving inverse problems is to use an iterative method. So in this, in these problems, in these methods, essentially you drop the regularization term and you just look at, say, your data fit term here. If you use some standard iterative methods to solve this problem, what you'll see here is that you get something called semi-convergence. So what is semi-convergence? This is for the image deblurring example. And what I'm going to plot here on the left is the relative error per iteration. And on the right, I'm going to show you the actual reconstruction. So this is for that deblurring problem. I should say, as a warning, right, in real life, you don't have this relative error curve on the left because this is a simulated example where I have the truth. So you can see that if I run a couple of iterations of a conjugate gradient or an LSQR method, the relative error starts to go down, and you see that the image, well, not much changes, right? This is after 10 iterations. The reconstruction is still not very clear, right? So you do a couple more iterations, so say 28 iterations, and the relative error is continuing to go down, and you see that your solution is getting better. So you think, okay, this is a great method. It's my picture is getting clear. So I do a couple more iterations, 85 iterations. What you start to see is that after some point, the relative error starts to go up again. And when you look at the reconstructions, the noise enters the reconstruction and corrupts the solution. So at first you might think that maybe you have a bug in the code or something is wrong. But in reality, it's doing exactly what it should be doing, right? It's actually converging to the inverse solution or the least square solution. And that is why you have kind of this noise in your reconstruction. So the motivation for developing a hybrid iterative method is to say, well, it's really hard to find a good stopping criteria for these iterative methods. It would be great, right, if we could stop down here when the error is the smallest or when the solution is clearest. But if I stop too early or if I stop too late, right, my image might already be corrupted or might still be blurry. So rather than try to find a method that could find that stopping point, we want to develop a hybrid method where the idea is that you would combine an iterative method with the regularization method so that you get errors that look like this red curve here that essentially decay but then stabilize. And the nice thing is that then it doesn't rely so much on the stopping criteria. Okay, so this is an overview of what does a hybrid projection method look like for standard Tikhonov regularization. So the idea, remember, of the hybrid is that you're combining the iterative method, which suffers from the semi-convergence, with the variational regularization, something like a Tikhonov regularization, which imposes some smoothness or penalty on your solution. So essentially, a hybrid projection method is an iterative method where at each iteration, you would first expand your projection subspace. So you're saying, I want to find a good subspace for my solution. And at each iteration, I essentially add a new vector into that space. Once I've created my projection subspace, I'm going to find a regularization parameter for that projected problem. Okay, so I don't want to look for the regularization parameter for the full problem because I can't, because A is too large, right? But I can do it for the projected problem because it's going to be smaller than my original problem. So I'm going to look for a regularization parameter for my projected problem, and then I'm going to solve the regularized, because I have this piece here, projected problem here. So I'm going to look in this particular subspace spanned by the VK and compute a regularized solution there. So essentially I'm combining two different types of regularization, right? I'm combining the regularization by projection and regularization by kind of the standard regularization term. Okay, so I wanted to also give you an overview of hybrid projection methods, because they've actually been around for about 4 decades now. To the best of our knowledge, the first journal publication was in 1981 by Diane O'Leary and John Simmons. There was a technical report by Bjork in 1980, but that one became a publication in 1988. So we attribute it to both of them. The ideas that they started with were to use the Golub-Kahan bidiagonalization with a TSVD type regularization. So they started, putting these two ideas together. Between 1991 and 2000, hybrid projection methods gained significant traction in the numerical linear algebra community, as well as some practical utility in seismic imaging applications. So a couple of key topics during that period are understanding regularizing properties of Krylov methods, stopping criteria reorthogonalization, some work on regularization parameter selection methods. A couple of the key players are listed here, but of course there are probably many more who have worked on these problems. Then in the period between 2001 and 2010, we actually saw a boom in the computational implementation of these hybrid methods, partly because of more computational resources and capabilities. We saw some new software come out, different methods on estimating the noise levels, implementations on high performance computing architectures, things like that. So a lot of work going on in actually realizing the benefits of the hybrid methods. And then actually in the last decade, we've seen a generalization of these hybrid methods to include more general regularization terms, to include different types of constraints, to be able to solve different problems. And also actually the connection to uncertainty quantification. We're starting to see, how can we take the advantages, right, of these hybrid methods, of what's going on with these low rank approximations, and use them to efficiently do, say, uncertainty quantification and sampling. So that's kind of hopefully that gives you an overview of kind of where we've been and maybe even of where we can go. Okay, so I want to spend the rest of my time talking about some of these recent advancements. I'll start off with this project that actually began at SAMSI a couple of years ago in a working group, where we developed these generalized hybrid methods with Arvind Saibaba. So this is the idea of the generalized hybrid methods. So John gave a nice introduction to Bayesian inversion and the Bayesian idea of how to solve inverse problems, where essentially you have this assumption that your variables are all random variables, and you include some prior knowledge on your unknowns. And so in that sense, what we're going to look at is the following scenario, where the assumption is that your unknown image or vector, whatever you like here, comes from a Gaussian with a mean mu and a covariance matrix here. So this is just the parameter, but there is a Q matrix here, which is my covariance matrix, prior covariance. And then I'm going to use the simple assumption about my additive noise, which comes from a Gaussian with this diagonal, say, covariance matrix. So you can write down the posterior distribution. We saw similar equations in John's slides, where essentially you can show that in this particular situation, right, where we have these assumptions, the posterior distribution is also a Gaussian, right, with a mean. So we'll talk a little bit about the mean here. In particular, this will be the map estimate, and with a posterior covariance matrix. And I think in John's slides, this was the L matrix. So here in this case, we have a Q inverse. So what we're interested in is problems where your prior covariance matrix, this Q, might be easy to apply, right? So matrix vector multiplications with Q are easy, but obtaining the inverse matrix, or even obtaining some symmetric factorization of either Q or Q inverse, might be quite difficult. I mean, imagine if the number of unknowns that you're dealing with is about 7 million, right? So this Q matrix is 7 million by 7 million. So computing that inverse or even a factorization might be computationally prohibitive. So we're looking at, how can we extend the concept of hybrid methods to deal with this scenario? Okay, so we're actually, even though I should say we do have some work on not just computing the map estimate, but also obtaining samples from this distribution. I'm not going to go into the details of that now. I'm really just going to focus on under this scenario, how do I compute an estimate of the map All right, so the map, this S sub lambda, right, corresponds to the point estimate, which corresponds to the maximum of the posterior here, this pi of S given D. And so if I just use the formula from the previous slide, rather than taking the maximum, right, I'm going to take a negative log, and I'm going to instead compute the minimizer. So I want to compute the minimum. I want to solve this optimization problem. Now, the standard approach would be to say, okay, well, I can just take this R inverse, I can take this Q inverse, take some symmetric factorization. It could be Cholesky, but it doesn't have to be. So take some symmetric factorization of it, and I can reformulate it in this form. And this is often called the general form Tikhonov problem, right, where you have this LQ matrix in here. So we can think of it as a transformation to standard form, where there's some work that refers to this process as prior conditioning of the problem. But remember, for the problems we're interested in, it's not possible to obtain Q inverse or LQ inverse, right? All I can really work with is matrix vector multiplications with Q. All right, so what we did was we said, okay, well, let's look at the normal equations that correspond to the optimization problem, right, that we need to solve. And we're going to do a different kind of change of variables. Okay, so this was the normal equations, and we did a change of variables where we set X to be this Q inverse times S minus mu. So I subtract off the mean. And then I have to also do a shift in my right-hand side in my observation. So rather than D, right, I subtract off A times the mean. And so we can see that the normal equations is equivalent to this system here. And the idea is that we will compute an estimate of the map, right? So this S sub lambda, right, as this mu plus Q X sub lambda, where X sub lambda actually solves this optimization problem here. So what are the main differences, right? So in this optimization problem, right, I no longer have A times S, I now have an AQ. Okay, so I have an AQ, which I need to be able to do matrix vector multiplications with efficiently. The other big difference is that here, notice that in the norm, I have the Q norm. I do not have the Q inverse norm because I cannot really work with the inverse, but I can work with Q. Okay, so now I'm going to tell you about a hybrid method that we developed in order to efficiently solve this optimization problem. All right, so this is based on something called the generalized Golub-Kahan method. So it really is just a generalization of the standard Golub-Kahan diagonalization. The idea is that you're given your A, you have your right-hand side B in this case, right? You have your R and your Q matrix. And so you build up your subspace. So you build up your vectors in V, as well as your vectors in this UK plus 1, as well as this bidiagonal matrix BK. I should make a comment about the size of this matrix, because if you remember, the original problem, my A matrix, right, might be on the order of millions, right, maybe million by million. But the BK matrix, this bidiagonal matrix that you get because you're doing this projection process, is actually k plus 1 by k. So if I'm at, like, say, the 100th iteration, right, this matrix is 101 by 100. So much smaller than the original problem. And so I have all of these nice relationships, right? I can also say where my solution space spans. It is indeed a Krylov space. And then the basic idea is that we use this gen-GK approach to project our problem down. This is the same framework, right? Once I've projected my problem down, I compute the regularization parameter using standard methods, because again, this is a small problem, right? It's a small problem. I can easily take an SVD of this BK here. And then once I compute my solution, I just have to work my way backwards, right? Once I get my ZK, I just work my way backwards to get the approximation of the of my solution, this SK. And so you can see here's a illustration with the kind of the standard LSQR type methods where you have no regularization, you get semi-convergence, you see the U-shaped error curve. But with the hybrid approach, if you are able to choose the regularization parameter appropriately, then you can get this flattening of the relative error. Okay, the next project I want to tell you about is with Silvia Gazzola at Bath, and the idea here is that we wanted to extend the hybrid methods to work not only for Tikhonov type problems or regularizers where you have, say, Gaussian assumptions, but more general regularization terms. So we looked at the LP regularized problem. So this is the same as before, but here you have the P norm regularization. Which actually there are a lot of different reasons why people want to look at these different P-norm regularizers. In particular, if you choose P equals to 1, you tend to get sparse reconstructions. You get reconstructions that can preserve edges. If you're dealing with image processing, right, the edges are important features. And so a lot of people have looked at these problems before, and there are many methods out there. I just give you a sample of the different types of methods that people have developed. But what we're going to do is we're following this idea developed by Sylvia and Jim Nagy on flexible Arnoldi-Tikhonov methods, where they essentially use a flexible preconditioner idea in an Arnoldi-Tikhonov framework. So we extended this to more general Krylov, hybrid Krylov methods. So the basic idea of the flexible method starts with an iterative reweighted norm problem, where you say, okay, I need to solve this L1 regularized problem, and what I'm going to do is I'm going to essentially approximate the one norm with a sequence of two norms, right? So a sequence of two norms here, where each time, as you can see, this L of S matrix, it's simple, it's just a diagonal matrix, but it changes based on your current estimate of your solution. So in a standard IRN method, you would essentially have an iterative method where each time you would just change your regularizer. Well, the really cool thing that Sylvia and Jim realized was that you can also think about this as a changing preconditioner, a changing right preconditioner, and therefore you can exploit methods from flexible preconditioning. And so we looked at something called a flexible Golub-Kahan process, which is actually closely related to some work out there on inexact Krylov methods. But the idea here is that you still want to build up a subspace for your solution, but the difference is that the subspace we're looking at, which is the ZK, right? It incorporates the changing preconditioner. So here you have an L1, L2, up to an LK, right, up to the kth iteration. And the other kind of different thing is that you no longer have this nice bidiagonal matrix. You actually are going to have to keep track of a upper Hessenberg matrix as well as an upper triangular matrix. But we're actually not too concerned about this in terms of the computational cost, because these are small matrices, right? They're K by K or K plus 1 by K. And I'm assuming that the number of iterations can stay modest. So the idea is that we use this flexible Golub-Kahan approach to generate my basis vectors, these ZKs. We have these nice relationships that allow us to project our problem down nicely to the smaller dimensional space. And then we solve our regularized problem, right, with automatic regularization parameter selection on the projected problem and work your way back up. Now, one of the great things about the flexible hybrid methods is that the solution that you obtain, your current solution, is immediately incorporated into your solution process, right? Because it allows you to essentially build your next solution vector. And then as with all of these hybrid methods, the other benefit is that you can choose your regularization parameter automatically. These things don't have to be predetermined. Okay, I guess quickly, I'll just give an overview of this third project on incorporating recycling and compression within hybrid methods. And this is with Eric Desterler and Julianne. So the idea here is that sometimes the number of solution vectors that you have to save can become so large that it becomes burdensome to store it, right? So if I run, say, p iterations of a Golub-Kahan biodiagonalization process, these vectors I need to store so that I can compute my solution in the end. And if each of these vectors is 7 million elements long, right, this matrix might get too much to save. And so the idea is that we would say, okay, well, let me take those vectors, let me compress them down. There are various ways to do the compression. You could use your bidiagonal matrix. You could identify important columns of that. But once you've reduced it down or compressed it down to a smaller number of vectors, then how do we continue the process, right? How do we, I mean, at that point, your solution is not good enough. How do you improve your solution? So that's what the idea here is of the recycling hybrid methods. You also, this idea might also work when you want to solve a sequence of problems, for perhaps say in an OED framework, right? You have to solve multiple inverse problems where your right-hand side might be changing slightly, or in streaming data problems, you can use this concept of recycling to improve your subspace. So just the general outline of how the recycling works. You start off with some vectors, so some WK-1, as well as maybe some initial solution. You construct an orthonormal set of basis vectors. You use something called the recycling Golub-Kahan biodiagonalization in order to construct an augmented subspace, so this VL tilde. And the VL tilde actually depends on your WK-1 and your S1. So it depends on the space that you're kind of coming to the problem with. Once you construct your new space, you can again compute the regularization parameter for a smaller problem, right? And then compute your solution in this augmented space. And then the nice thing is that you can run this approach multiple times. Suppose you're still not happy with your solution, you can compress it, build it back out again, compress it, build it back out again, and so on. Okay, so let me quickly just summarize. So I talked a lot about these hybrid projection methods. They're nice because they're efficient in the sense that you only need matrix vector multiplications with A and A transpose. You can actually develop Arnoldi type methods where you really just need matrix vector multiplications with A, but then you need a square system to do that. They're automatic because you can choose that regularization parameter during the iterative process. And it's not so critical what your stopping criteria is, because if you stop a little bit too late, your regularization essentially takes care of any error entering the solution. And actually, I didn't talk too much about this, but there are some nice equivalence results, some theoretical results that show that these hybrid projection methods have very nice connections to standard iterative methods applied to the regularized problem. So I gave you an overview of these generalized hybrid methods, which are great for including different more general priors, flexible methods for solving LP regularized problems, and just the basic idea of the recycling with compression, which we think can be used in a lot of different cases. And hopefully there will be more hybrid methods to come from this working group. So thank you so much for your attention. I'm happy to take questions.
Thank you so much, Julianne. If there are questions, once again, I ask people raise their hands or type it into the chat window. Thank you very much.
I have a quick one if I can ask.
Please go ahead.
It's sort of suppose we have a D by D covariance matrix, and we have a metric on the space of covariance matrices, and the metric is scaled so that it doesn't depend upon D. If we have some very high dimensional matrix, if D is very large, and we look for some ball around the covariance matrix we have, is it going to be very likely that there's an easily invertible matrix within that small ball, or is it very unlikely that there will be an easily invertible matrix within that ball?
So that's a good question, and I don't know the answer to that. My guess is that you probably could find a covariance matrix that is invertible close to your covariance matrix. I mean, I guess you could always just add something small, like a nugget or so, right, to make it invertible. But in terms of getting the inverse in order to use the existing methods, that is I don't know.
Well, that's the idea. If it turns out that as your dimensionality explodes, you have high probability of finding an easily invertible matrix close to the matrix you have, then that just is a fine way to start the approximation process the way John was doing. But I was just curious. Thank you.
Yeah, thanks.
All right, please unmute yourself and go ahead and ask your question.
Okay. Actually, this was just a quick remark on David's question. So what is the case is that many of these problems that come out of integral equations often have special structure, or at least in some ideal case, they have special structure. And for those, I mean, if you go back in the literature 10, 20 years, there are many fast solvers based on the Kronecker structure, all kinds of other structure. So what might be possible is that maybe you were talking about the covariance matrix, not about the matrix itself.
I was thinking about the covariance matrix specifically because that sort of arises naturally in my world, but maybe the more general question is worth thinking about too.
Okay. Yeah, so for some of these matrices, there might be very good like preconditioners because there are nearby problems that have very special structure.
Other questions for Julianne? Well, if not, let's end this session.